Okay, so we consider the same equation, x minus 4y plus 7z equal to 5. We want to know how to write the solution set. And previously we gave a geometric description of the solution set. So that would actually be a way of describing the set. It's a plane passing through the point 5, 0, 0 and perpendicular to the vector n, which is 1 minus 4, 7. So sometimes actually you'll be asked to describe geometrically your solution set. Usually that comes from obtaining the set algebraically and getting the geometric description. Here we're kind of going the other way around. So now I want to show you algebraically how you can recover the solution set. So how do you do this? You assign, well, let me go through how we got some points that are part of the solution set before, right? So maybe you don't need to write this down, but before what we essentially did, we assigned some values to y and z, and then we solve for x to get the coordinate of the third coordinate of the point. So for example, if I assign values of 0 and 0 to y and z, clearly x is 5. So I get 5, 0, 0. If I do this again, I assign maybe values of 1 and 0 to y and z. If I replace in the equation, I get x minus 4 plus 0 equals 5. So x is now 9. So 9, 1, 0. And I can keep going like this, right? I assign values of 0 and 1 to y and z. And now x is going to be minus 2. As in minus 2 plus 7 is 5, yes. So minus 2, 0, 1. And I can keep on going like this. So essentially, what am I doing? I'm assigning some value to y and z. We'll call this s and t, and we're going to solve for x. Okay. So let y equal to s. So s is one of those values here, right? Then I'm assigning to y, and z equals t, and this is me assigning these values to z. Okay, so I'm kind of replicating this, but in a very general way. So I'm not specifying what s and t can be. They can be any of my favorite values, where s, t are some real numbers. Now solve for x. How do I do that? Well, I just replace y by s, z by t, and I solve for x. So x is 4s minus 7. Actually, I'm going to put the 5 in front. So 5 plus 4s minus 7t. And I'm going to collect the solution I get, which is actually going to be a solution set because I haven't specified what s and t are going to be. So x, y, z is going to be of the form 5 plus 4s minus 7t. Y is s, z is t. And this is understood. If I don't write it down, it's understood that s and t are real numbers. So this is the solution set. This is how we're going to write it algebraically. Essentially, you can recover infinitely many points by assigning, just like I did there, your favorite values to s and t. Sometimes we also want to write this in vector form. So in vector form, how does the solution set look like? Well, I'm going to put x, y, z like that. I could put in row vectors too, but I like column vectors. So 5 plus 4s minus 7t, st like that. And sometimes we like to split it up. Well, actually, let me put the t, line up the t with the 7t up there, just so that you see how I'm going to split up my vector. I'm going to write it as 5, 0, 0 plus 4s s0 plus minus 7t 0t. So now I've written it down as the sum of three vectors, one which is the constant vector, one which is a vector that includes the terms that have an s in them, and the terms where t is involved. And the other thing we like to do is we like to factor out the s and the t, like that. And what do I get here? I get really, like, maybe let's rewrite this. Like XYZ is, let me just rewrite everything like that. And if you've been working with planes on enough, you recognize that here you've got, this is the vector equation. Actually, the whole thing here, that's the vector equation of a plane, right? It's not surprising it's the vector equation of a plane. We know that there are solution sets of plane, right? But now it's in vector form. So this is what the algebraic solution gives us eventually. You see, this is actually a point on the plane, and those two vectors here, right, the s and the t, they allow us, well, remember, the vector equation of a plane, you've got your point, and then you've got two vectors, maybe v1, v2, that allow you to move within that plane. So those are two vectors that are contained in the plane. So so this part here, the last two terms, they actually form a linear combination of v1 and v2. So this is algebraically how you can write down the equation of your plane. Let me just show you that you can check that this makes sense. Remember, right? We knew the vector n that was perpendicular to the plane. What was it again? N was, you just have to collect, 1 minus 4, 7. You collect the coefficients of x, y, and z. So if the values that we obtain, like v1 is what, 410, and v2 is minus 701. If this is correct, v1 and v2, they should be perpendicular to n. So we can check that. If I do v1 dot n to check that they are perpendicular, I'm going to check that the dot product is 0. Let's verify this. 410 dot with 1 minus 4, 7. That's 4 minus 4 plus 0, so it's 0, yes. And if I do v2 dot n, it's minus 701 dot product with 1 minus 4, 7, and we get minus 7 plus 0 plus 7, and we get 0 again. And so those vectors here, right, they're perpendicular to n. And this is the exact same point that we got previously when we gave a geometrical description of our plane. So essentially, writing down the solution algebraically, it gives us the vector equation of that plane. Now I want to look at a second example. Here I've got two equations and 3 unknowns, 3 variables. So here's the system. 4x minus y plus 3z is equal to 3. 4x plus y plus 9z is equal to 5. So let's say these are equations 1 and 2. So what do we have here? Well, the first, well, maybe a quick comment. Are these parallel planes? Because if those are parallel planes, maybe there are no solutions. How do we check this? Well, there are 2 things you can do. You can look at your normal vectors for each plane. Okay, and if they are proportional, then you have parallel planes, and potentially maybe overlapping planes if the constants are proportional in the same way. But here, those are not proportional, right? So n1, n and 2 are not proportional. So they're not parallel, right? Those are not parallel planes. So this is something we can just see from the equations. So what does that mean? Like, that means I've got one plane there, and I've got another plane that's not parallel to that plane. So it's going to intersect that plane somehow. Maybe like this, I don't know. Okay, just keep going. Okay, so already I kind of know I'm going to have infinitely many solutions along a line. So I can expect in my vector equation to have one parameter, because if I have two parameters, right, it's the equation of a plane. We saw that here. If I just have one parameter, it's going to be the equation of a line, because there's going to be movement only along one direction. So let's see if we can observe this by solving algebraically this this system. Okay, what I can do is I can remove. I'm going to teach you, by the way, a very easy and systematic way of solving these linear systems, but that's in the next section. So right now I'm just showing you how we can make our way to our solution. But it's not, if you wonder why did you do that and not that, well, actually there are a whole bunch of things I could do. Okay, this is one possible way of getting the solution set. So right now it's not so important to understand how I'm getting the solution set as to the way it's expressed. So to get the solution set, I'm going to remove one variable from the last equation. Okay, how do I do that? Well, look, I could actually remove 4x by subtracting equation 1 from equation 2. So I'm going to do equation 2 minus equation 1. This is what I'm going to do here. So if I do equation 2 minus equation 1, 4x minus 4x is 0, so it disappears. Y minus minus y, that's 2y. Right, so I'm doing this minus this. Huh? So I'm subtracting from bottom to top, okay? 2, so this is 2, right? 2y. 9z minus 3z, that's 6z, and 5 minus 3 is 2. So I've sort of removed, I get a third equation, okay, that's been derived from the first two. Oh, you know what? I'm going to call that equation 4, and for 3, I'm just going to recopy the first equation. 4x minus y plus 3z equals to 3. Actually, 3 and 1 are the same. So this is the kind of new system that I get. Okay, and now I'm going to let z take on some arbitrary value, and I'm going to try to see if I can solve for the other variables. And solve. So I'm going to solve for equation 4 for y. So I can do that. So 2y plus 6t is going to be equal to 2 once I replace z by t. And I'm going to send the 6t on the other side and divide everything by 2. So y is going to be 1 minus 3t. So if I choose t equals 1 for z, okay, then my the y value for is going to be 1 minus 3, so minus 2. So that's going to be the y coordinate of the point in my solution set, and then I can recover the x. Okay, so by letting things be arbitrary here, like t, I'm going to recover all the points in my solution set, and I'm going to do the same here and solve for x now. So replace x, I'm going to replace y by 1 minus 3t and z by t in equation 3 or 1, which is the same. So if I do this, I get 4x minus 1 minus 3t plus 3z, so 3t equals to 3. I'm going to try to send everything on the other side. So that's going to be 3 minus 3t. Careful here, careful. This is what? This is minus 1 plus 3t. So plus 1 here, minus 3t on that side. So 4x is 3 plus 1, 4, minus 3t is minus 3t minus 60. And I divide everything by 4. So this is the x that I get, and I am going to collect everything now. So x, y, z. So this is my solution set. The solution set is the top. X is 1 minus 3 half of t. Z is y is 1 minus 3t, and z is t. And once again, I can break this down into the constant part and the part that involves my variable. And I can factor out my t. And what do I get? I get a solution set with only one parameter. One parameter means I'm only moving in one direction, right? If I read this correctly, it means I'm starting at 1, 0, 0, and t times minus 3 half minus 3, 1 is going to allow me to move in the direction of minus 3 half minus 3, 1 in order to attain any point that would be on this line. Right? So if the origin's here, right, then the first thing that I compute the vector 1, 0, 0. It takes me to the point 1, 0, 0. And then I can move along, right, so I'm doing this. Then by adding a multiple of v, I'm allowed to attain any point. If I want to get here, probably I'll add 2 times v, so t would be 2 here if I want to get there. If I want to get here, I would be subtracting v, so it would be minus v. Okay, so this way I can attain any point on that line. So this is a line. So that would be the geometric description of this set. It's a line passing through, so this is algebraic, right? And this is geometric. So sometimes in the book they'll give a geometric description. This is what they want. A line passing through the point 1, 1, 0 and parallel to the vector minus 3 half minus 3, 1. So this is our solution set, and we're getting a line. By the way, it's not surprising. This is what we were expecting. Remember, we're expecting to get a line here for our solution set because we've got 2 non-parallel planes intersecting. Okay.